so much, everyone, for coming. Hi, my name is Raúl. I'm from TJ, Baja California, in Mexico. And I'm here to talk about the Gleam programming language. And I'm here to talk about actors. So what is Gleam? The Gleam programming language is a language for the virtual machine, the Beam. And it's an interesting language in the sense that it tries to add types to the ecosystem of programming language. We know that Erlang is not typed. Elixir is getting there with types, but still we don't have like a type system like Gleam does, which is like an SML-based type system. So what I want to do first, before starting the actual talk, is to do a mini tour through Gleam. If you have already done Erlang or Elixir before, you will find Gleam very familiar, and I feel like you can learn Gleam in an afternoon, in a couple of hours. So if you are interested in the language, I think you can learn something from these first slides. So for example, here we have a complete Gleam program. And what this program is about is that at the top, we have a couple of imports from the standard library. Then in the middle, we have a constant, a module level constant, just like in Erlang or Elixir. And here we are defining just a list of names. And then the entry point of every Gleam program is the main function. So right now, what we are doing is we are just shuffling between the list of persons. We are pattern matching with the list and getting the first element of the list. And then we are printing, hey, Chouza, or hey, Roberto, hey, Miguel. So that's what this program does. And if I go to Gleam and I try to compile it, this will happen. Basically, the compiling is saying, hey, you have a list here. Are you sure you have not covered the missing pattern, which is an empty list? Because if this is an empty list, this will crash. So be careful. But thankfully, we know that Erlang and Elixir are very assertive languages. The languages in the Vim have this property. And what we can do to make the compiler trust us, because of course, this is a constant. We know that the elements are always going to be 4 elements in this list. We don't need to worry about this check. So we just say, let assert. And with this, we let the compiler trust our decision in that we can safely pattern match this. So talking about assertion, I think one of the things that I do Elixir on a day-to-day basis, and my favorite feature by far on Elixir is just the capacity to be able to pattern match on maps. Because maps in Elixir are so cool, they can be used for almost everything. They can be used for configuration. They can be used for storing data in maps. And we can use them to pattern match and be very specific about the pattern matches. So for example, here we are creating kind of like an interface for spawning an ETS table. And what we are passing in is a configuration. The configuration is just a map with the name, the type of access that we want in this ETS table. But we also can pass less data and have a couple of defaults that work for our system. So what if we want to translate this to Gleam? The good thing is that we can translate it we can just translate this to Gleam. And let's show a little example. The first thing we need to do is to interface with Erlang. And the way we can do this is by using an external. With this external, we can pretty much call anything in the Erlang virtual machine or Elixir virtual machine, or even JavaScript, if we want to, if we are running on the JavaScript virtual machine. And then we create a small wrapper around this call. So for example, for ETS new from Erlang, we just create a function called ETS new and the options that we want to pass to it. So then we have to convert from Elixir to Gleam. So we use Gleam syntax for this. And there's a little problem here. And the first problem is that before we were pattern matching on a map with Elixir, but in Gleam we don't have maps, not like in Elixir. There's no literal syntax for maps in Gleam, and there's also no way of pattern matching with maps in Gleam. Why is this the case? Mostly because in Gleam, we will not do pattern matching with maps. Maps here are more like a collection, an infinite collection of items. And they have certain limitations. For example, in Erlang or Elixir, we can create a map, and the keys of the map can be anything, and the values of the map can be anything. Here in Gleam, again, it's more like a collection. So the key type has to be one thing. In this case, it's just a list of a dictionary of numbers. And the values have to be another thing, in this case, strings. So there's the first limitation. We can try with other collection data structures. For example, we can try with list. And actually, the list will work here. But the only reason why it will work is because all the parameters that we are passing are atoms. And with lists, as long as all the elements of the list are the same, in this case, for example, up above here, it's booleans, and below there, it will be atoms. That would work. But if we needed like a more complex API that needed to hold many types of values together, this will pretty much not work very quickly. Thankfully, in Gleam, we have tuples, and tuples can have multiple types in each tuple. So for example, here we have an example tuple which can have a string, it can have an integer, it can have a boolean, but then we run into another problem. Again, tuples behave more like sets, not necessarily like parameters for configuration. So the first case, the compiler will encounter this and say, hey, your first parameter has a length of 3, but your second has a length of 1. This is incompatible. We cannot do this in Gleam. So the way to do this in Gleam is that we will not use collections, not the normal collections we use in Erlang or Elixir. What we will use is we will create a new type. So for example, here, we created the table config type, and then we have two constructors. The first one is called custom, and it has two parameters, a string and a list of options. And the second one is just a default, and it's just a string. And in this way, we can just pattern match these records and then pass the options that we need to the new ETS table. So more or less, this is how Gleam programs look. It's a very simple syntax. If you already know Erlang or Elixir, you pretty much know, I guess, like 70% of Gleam, or maybe more. And for example, I showed the last example. It was for configuration, but this doesn't mean that types restrict us to have like a very set, to just have a set of values. Types can be very flexible. And in this example, I want to show this flexibility by just having like a tree. And this tree data structure, we have the tree type, and you can see that you can pass in a parameter x. This is a generic. This means that we can make trees of integers, we can make trees of strings, we can make trees of any other custom type that you want. And then the constructors are node and leaf. And of course, the node is recursive, so we can iterate through it. And then the leaf is just the value that we want. And then we can create a very simple traversal algorithm to just traverse through a custom data structure that we want to use. So types can be very flexible, and usually this is the way to go with Gleam. So now, let's start the talk, which is getting to know actors in Gleam. And in a similar way as we saw before, like certain things in Gleam have to shift because of types. And there are a couple of concepts that we must learn before learning how an actor works. So the first concept I want to talk about is that of the subject. What is a subject? The subject is basically a new type. It's a wrapper for a PID in Erlang or Elixir. And this is more or less what a program that uses the subject looks like. I'm going to go very quickly with this, which is the type at the top is just a custom type that I defined. It's called exists, and it has two constructors, something or nothing. So it can have two values. Then I'm using a function called process.newSubject. This subject is very similar to the function self in Elixir, which returns a PID. So new subject will return a subject type, which is a wrapper for the PID, which is just a reference to call the current process. And we will store that subject into the variable, and then we will try to send a message to this subject, to ourselves. So in this case, we are sending the number 1, and then at the bottom, we are just receiving this number. So if we receive the number and it's above 0, we just return something. If it's anything else, we return nothing. It's a very simple program. And something very interesting about this type is that the subject is not only a wrapper for a PID, it actually becomes typed. And the way it comes typed is by, for example, here, we can see it's a subject of an integer. So what this type is saying is, okay, what is this subject about? And this subject is about integers. So for example, if we can see that we are sending the process number 1, and we try to change the type, the compiler will say, hey, there's a type mismatch here. You are trying to send an integer, but here I found a tuple. So that can become very limiting, that if we declare a new PID, that we restrict the types that way for the messages. So what we usually do is that we just create multiple subjects. So for example, here we are creating a new subject, and this subject is about booleans. Both subjects have the same PID because we are defining them in the same scope. And then we can send this same process an integer or a boolean. And then we have multiple receives for each subject. And at first, this can work very well, but then if our API, or depending on our application, if this starts to grow, the multiple receive parts is not necessarily ideal, because we don't want to have multiple APIs for a single thing, maybe. So there's another concept I want to talk about, which is that of a selector. A selector is a special case for receiving multiple messages for multiple subjects. So let's look at an example, and let's retake the previous example. We have a subject about integers and a subject about booleans. We are going to create a new subject type, sorry, a new selector type. And with the selector type, we are going to bind the different subjects with different mappers. So for example, for subject A, we are going to create a binding for this function which maps integers to the final type that we want. And for subject B, we are doing the same for booleans. And now, instead of doing the process received, we are going to use process.select. We are going to pass in our selector, and now this process can both receive integers and boolean, whatever message comes first. So this is usually the way we'll do that kind of like that kind of construct with Gleam. So finally, we can talk about actors. And I mean, usually I feel like, well, let's start by this. So actors are very similar to gen servers in Erlang or Elixir, but they are not gen servers. They are a re-implementation of gen servers. You have seen before that we are still working with processes with Erlang. It's the same concept. So this is just a reconstruction of a gen server, but in a Gleam style. And the name for it is an actor. And usually gen servers or actors, I feel like, consist of 3 parts. We have messages, we have a behavior, and we have the internal state. Here we can very clearly see that we have a type with messages. We have the behavior, which is the constant loop that this gen server or actor will go through. And then finally, when we are initializing this actor with the number 0, which is our internal state. And the way we can use this is that we can start sending increment message to this counter actor. So it can hold the current count of numbers. So we are sending first 3, and then we are sending 7. The current count should be 10. And we still need a way to retrieve these values or make this counter actor useful. So the way we can retrieve its internal state is just by creating a new message type. So we create the current constructor, and the current constructor has the color as a parameter. Then on the loop, we just add the current color as part of the loop. And we are going to send back the current count to the color and then just continue the actor as normal without changing the state. And then for making a call message, instead of using process send, we are going to use process.call with the current subject. So that's pretty much how an actor looks like. It's a very simple concept, but it's very powerful. And I want to show this power with a very simple demo. Well, I'm not sure if it's simple, but it's a demo. So this is a demo for a card game that I wanted to make from long ago. And for example, here I can pretty much launch a new game. And I can start just playing. So I can start clicking on the cards. And then I can start clicking on the player 2 cards. And then I can just start placing cards And I mean, this works, but not for very long because I don't want to play against myself all the time. So what we can do is we can create a single player session. And on this single player session, I can just play with a computer. The computer, of course, is just another actor. And I can just play the cards with a computer. And when I am done with my turn, like this, the computer plays its turn. And you can go like this until one of the players wins. Of course, we can also create, if I already created an actor for the computer, why not make two computers play the game? So we can do this. We can enter the game and see what's happening over here. We have two actors playing each other. Both of these actors are playing in another actor, which is the session. The session is a thing that holds the state for the game. So I just want to more or less explain how this works and how this is wired up. So here I have a couple of diagrams to show this. So for example, when I create a new one-player game, what happens is that I post that I want to create a new session. The session gets created. A new game state is stored in this session. And then what I do is that I translate this, this game session, which is just a Gleam data structure, into HTML. And after that is translated to HTML, I just render a static site on the web page. So this is the first step that happened. When I created the session, I can either create 1, 2, or 0 computer players. But I also registered this session in a session registry, which is another actor. And this session registry works more like a database. I didn't want to have like a formal database. I wanted to do it with actors, and that's the reason why session registry exists. And right now I'm using it as a database of subjects. So, okay, after the page is mounted, what the client is going to try to do is to upgrade the connection to a WebSocket. And when that happens, the socket actor gets created. This socket actor has a reference to the session, and also this socket actor gets registered in a new socket registry. Why is it a socket registry? Because, of course, multiple sockets can exist in the connection. So, for example, if I went and copy-pasted this over here, and I started to make my moves for the cards I want, you can see that, well, we have multiple sockets, we have multiple clients, all playing the same game. So what will happen is that when one of the clients registers an action, like for example, play a card, it tells the socket, the socket tells the session, and then the session tries to update the state. If that's successful, it will return the state of the subject, it will return the state to the socket, and then the socket will try to notify all the other related sockets that, hey, there was an update, so that all the sockets can get updated in all of the browser clients. So at the end, more or less, this is what the architecture looks like in terms of actors. We can have multiple sockets, each one is an actor. We can have multiple sessions, each one an actor. They all get registered either in the session registry or the socket registry, and we can have 0, 1, or 2 computers per session. And of course, one final thing, these are actors, these are processes, and of course we have the concurrency capabilities of the Beam. So we can very easily just spawn thousands of processes and they can all be playing at the same time. And this is the last part. I want to talk like, what's the shutdown story here? Because if we see the current games are going, as long as the game is still like in play, I can still interact with it. So I can still make moves. But when the session is over, when the game ends, well, this screen gets displayed, showing the score. But there's now like really nothing to interact with. The game is over. So there's nothing here I can do. And what's happening here is that this is actually just static render content. When I detect that a session is over, I just render a static page. There's no need for interaction. So the shutdown story, how this works, is that basically we have the session, and almost every process, the socket, the computer players, the registers are monitoring the session. And when the session goes down, what happens is that the session detects that the game ended and then shuts down. Before shutting down, it compiles the current game state into HTML and tries to store that in this new component here, which is called CopDB. What is CopDB? CopDB is really cool. It's an Elixir database. And I want to very quickly show how this looks like, because this talks a little bit about the interoperability with the Beam. So here, for example, we have this is the project of this demo. So here, for example, I have the CopDB dependency declared. This is an Elixir library that was downloaded from Higgs. And then I have, for example, over here, I have a store, which is an Elixir module, and I have a store, which is a Gleam module. This Elixir module lives in my Gleam project, and I can just create Elixir in my Gleam project. And then I have this store.gleam, which is just a wrapper of the interface I defined here in Elixir. So this is pretty much just to say that Gleam is very interoperable. We can use Erlang modules, we can use Elixir modules right in your Gleam project, and you can just build wrappers so you can use them in your Gleam code. So this is how the HTML gets generated and gets stored into CopDB. And after it gets stored, the session disappears. We no longer need it. The data lives in CopDB. And now all the other processes register a process down message. And after that happens, there's nothing to do here. We just deregister in the current registries, clear all the processes, and then the socket registry gets the last socket down message, and then it's gone. And of course, we want to keep the client as it is. There's no need to change anything over there. The only thing that happens is that JavaScript will detect that the WebSocket connection went down, and it just stops. And after we try to do like a re-request with a get, like get the game 234, we are just going to return the HTML from the router. So pretty much this is the end of the presentation. What I would like to do right now is a couple of plugs for the Gleam community. So the first one, if you like what you saw with the Gleam language, you can go now to tour.gleam.run. And you can see the language tour. This is an interactive language tour, and you can learn the language very quickly here. So I really recommend that for learning if you are interested. Also, if you are interested in more of the community or how to build, how to contribute to the different libraries that are being developed right now, you can go to the Discord. It's a wonderful place full of lovely people where we talk mostly about cats and cafe. And finally, a big announcement that this week, Gleam version 1 was released. And I feel like this is a very strong indication that Gleam is pretty much ready for production. Then I want to talk a little bit about the web ecosystem because it's important. It's how I built this application. For this application, I use the Mist web server, which is a web server where you can do normal REST requests or web sockets. The Gleam HTTP, which is a middleware with useful functions for just having a request structure where you can pass around data. And finally, Nakai, which is a library that lets you transform Gleam data structures into HTML. And all of those three were very useful. Thank you so much for the creators of these libraries. And also, I want to say a little bit about Lustre and Wisp, which is our new upcoming libraries for this. So Lustre is Elm inspired, so if you like Elm, you will like Lustre. And it's very interesting in that it lets you do both, you can compile it to JavaScript and you can let your web components live in JavaScript, or you can compile it to Erlang and let your components live as server components in Erlang. And they can be static components, they can be live components, so that they can be connected by WebSockets, or maybe other transport systems. So it's a very exciting library that is coming and is being developed. And finally, Wisp. Wisp is another library which tries to wrap up everything into a nice package. The good thing about all of this is that all of this is interoperable with each other. So finally, thank you so much. for listening.